Okay, so as I told you that we have the first analysis of the building, and this is the summary of the first analysis of the building. Second, we have to improve that building. And what do we have to do? First, we have to increase the thermal insulation by 2 inches. Okay, so we apply 2 more inches on the roof, the wall, the basement. So everything has 2 more inches of thermal insulation. And what do I have to do? If you have already this Excel file, then you have to save as, because we need another one. I don't want you to lose the first analysis. So save this Excel file as improvements, okay? And now in this Excel file, we don't have to find the location. We don't have to find indoor and outdoor temperatures. This is the same. But in the wall, we have to change the thickness of the wall. So if by default you have 6 inches, and now you have 8. And if you have 8 inches, here you have the total thermal loads with 8 inches of thermal insulation. Okay, quite easy. We only have to change this cell. We have the same materials, but we have 2 more inches of thermal insulation. For the roof, it might be slightly different, because for the roof, as you know, we have the rafters and thermal insulation. So we have rafters, and then we have thermal insulation with a different material. Okay, and then another rafter. And then remember that we had what the materials, we had an air cavity, a gypsum, and then another air cavity here, and the asphalt shingles. So if we have this, we have another air cavity here with a different color. Another air cavity underneath this, and there was a gypsum board or a gypsum false ceiling here. And then we have the asphalt with a different color. Okay, so that was the roof, and you had to calculate the thermal transmittance through the rafters, through the thermal insulation, and then the U average. But now, if we want to add 2 more inches of thermal insulation, probably we have to increase the thickness of the roof. So we have to move this up. And now I have to apply 2 more inches of thermal insulation here. Okay. So basically, I'm adding a new layer, and that layer affects the part of the rafter and the part of the thermal insulation. So on this Excel file, above the fiberglass for the rafters, we have to insert a new layer, and this is it can be another 2 inches of fiberglass. The thickness is 2 inches, and the thermal conductivity is the same because it's thermal insulation. So it will be the same thermal conductivity. And here we have to drag this to calculate the thermal resistance. So the thermal resistance has changed, and the U value has changed, and we have to do the same thing here where the rafters are. Okay, so we have added this extra layer of thermal insulation, of 2-inch thermal insulation, and those values have changed, and the U average has changed, but the total area didn't change, and the thermal load changed as well. Okay, so that's what you have to do with the roof. And from the construction point of view, it makes sense. If you are working in an old building and you buy an old building with a flat roof, the first thing you have to do is to check whether the flat roof is good in terms of water leaks, because the waterproof layer can be damaged or whatever. You have to check the roof. Probably if the building is too old, you will have to change the waterproof layer on the flat roof. So you can, at the same time, you can do this. At the same time that you remove the existing finish of the roof, you can add more thermal insulation and then do it. Okay, so this is something that makes sense. The other option would be to place this thermal insulation underneath the existing ceiling. But with this option, you are losing free height. So the free height, the minimum, it's 10 feet. So if the ceiling is at 10 feet above the floor level, you cannot go below that because the minimum has to be 10 feet. Okay. So if you have high ceilings, probably you can do that. You can apply the thermal insulation indoors. And working indoors, it's always easier and cheaper because people working indoors, first, they are safe. They are not suffering the rain or the snow or cold temperatures. So the working conditions are better. But sometimes we can't do that. So if we can't reduce the free height that we have in our ceiling, then we have to work outdoors. Anyway, indoors or outdoors, we need 2 more inches of thermal insulation on the roof. Then what about the windows? We have to replace the windows. Well, first we have to do that for the basement. On the basement, we have to apply 2 inches of thermal insulation. If you remember, we used this column. Well, the basement was, it has like an inch of thermal insulation at the top, on the roof, no, on the wall and the floor transition. And then the rest of the basement wall was uninsulated. If we add 2 more inches, well, probably we can take all these values from this column. Okay, so in this case, some of you have already done it, okay, but now we are taking all the values from this column. And now the total, this is E, okay, so it's this column. We have to drag this down. There. And now this value has changed and the total thermal load has changed. Okay, so on the basement, what we have to do is to consider this column, not this first row and then the uninsulated column. But if we apply 2 inches on the basement wall, we have to use this column. Okay. So here we have worked with the walls, the roof, and the basement. And now we have to work with the windows. So for the windows, we have 2 things. First, we have to replace this window with the triple glazing. And we have to calculate the solar heat gains through the windows. Okay, so for the windows, we have 2 measures. We have to replace the windows. And we have to select a new U value from the catalog. I'll explain what the catalog is. And then we have to calculate the solar free heating through the windows with a solar heating coefficient from the catalog. Well, okay. So what is a catalog? Well, first, what are glass manufacturers? Do you know any glass manufacturer in this area of the world?
Renestate glass.
What?
Renestate glass.
Yeah, but those are when it comes to glass, we have the glass manufacturer, the one that deals with this material, and they deliver huge panels, and huge, I mean 30 feet by 20 feet, something like that. And then Renestate glass, they cut this and they assemble the double or the triple glazing with the spacer and all that stuff. Okay, but I mean if you know the name of the glass manufacturer, the one who manufactures the raw material, not the window itself. Well, if you don't, that's what I'm here, because I'm going to let you know that there are only probably 4 or 5 big glass manufacturers in the world. So in Europe, 90% of the glass comes from Saint-Gobain, something like that. So this is a French brand, and well, they are multinational. They are a monster company, and they manufacture glasses for everything, for buildings, for cars, for bottles, or even the glasses, the sunglasses, whatever. So they manufacture all the glass that we can use in any industry. Okay. This is in Europe. So in Europe, they are this is the most important company in Europe. In the United Kingdom or in the United States, we have 2 companies. We have Pilkington. Pilkington Glass, Pilkington. Okay. They have branches mainly in USA and Canada, and also in the United Kingdom. And well, they manufacture, this is what we are looking for, the float glass. Float glass is what we use in buildings. And then we have the automotive glass. So it's different because the glasses in cars or in vehicles, they are not flat. The windshield is not flat, it's slightly curved. And the float glass is something that manufactures like these flat panes that we have in buildings. Okay? So this is the float glass operation. So they manufacture a lot. And then the other company that works in the United States is Guardian. So here we go to products. And well, so this is what they do, and they have innovative smart glass technology. Yeah, we have these kind of things. Okay, so in glass we have innovation. It's glass that tints on the wall in response to the sun, or better yet, without your filling response to the sun. Yeah, that's cool because in theory, the glass changes its color. And we have blinds to protect us from the unexpected sun. But well, there are smart glasses now that can change the color, can change its color as we receive. It's like the sunglasses that turn darker. So we can have these kind of glasses in windows now. Very expensive. But well, there's always innovation. Okay, so usually when you open the website, they display the most innovative product that they have. Okay. Anyway, this is Architectural Glass Solutions. We are this Guardian. This is the logo, and here in products. If we open these products, these are the glass types. We have all these, solar contour glass, low emissivity, float, residential glass, mirror, decorative, automotive glass, appliances. This is for bottles and whatever. Bird-friendly glass, I don't know what this is, and laminated glass. The laminated glass, it's safety. Let's talk about this. Okay, so when we have safety glasses, that means that you try to throw some of the glass, and the glass doesn't fall. It's broken, but the glass stays. So this is what we have in banks, or even in cars. We have this kind of laminated glass. So that means that they have a higher mechanical resistance. It's required for safety glasses. And what is laminated glass? So we have glass interlayers. So that means we have 2 panes of glass, and in the middle we have glue that sticks to glass panes. So when we throw a stone, we grade one of the panes that is glued so it doesn't fall. Okay, because people, well, people may be affected not because the glass itself, but because imagine that happens in a window on the third floor and pieces of glass fall on the street and they hit you. So you're dead. Okay, so that can happen. So that's why in skyscrapers and high-rise buildings we have safety glass, and even in handrails, in transparent handrails, we have this safety glass so that if one piece is broken, the glass don't fall because it's stick to the other glass pane. So this is the laminated glass, and then we can have a double laminated glass. Okay, so a laminated glass is a glass that has two glass panes. This is the first one. Then we have something here. And between these two glass panes, we have something very thin, usually transparent. Okay, so we don't notice that we have something here. We have this glue here. So this is the laminated glass. Then we can have the double laminated glass. Okay, the double glazing is two glass panes, and here we have a gap in the middle, and then we can fill that glass pane. This is the spacer. And then we have something here. Like this. Okay, so that would be the double glass. We have air or argon. So we have talked about this before. Here we have air or argon. Argon, it's better, it's more expensive. But here we have a gap, it's filled with air. These are the glass panes. And here we have a spacer. And this is silicone. And this is a sealant. It's something that connects two panes and at the same time prevents water from entering this air. Okay, so that would be the double glazing. And then if we want a triple glazing, we have three glass panes with two spacers and two silicone. Okay, so that would be the triple glazing, and that would be the double glazing. And both are laminated. If we want a non-laminated double glazing, then we remove this and this, and that will be a non-laminated double glazing. This is a laminated triple glazing. Sometimes we have this laminated glass outdoors because we don't want to, so usually we don't have these indoors, because indoors, even if that glass breaks, it's very unlikely that it can affect someone because of the height. But if that happens on the third floor and the glass hits you, then you have a problem. Okay, so that's the difference between double glazing and triple glazing. And this is, we have the material itself, the float glass. So this is the float glass. Then we can have the laminated glass for security or for safety. We have here this glue between two glass panes. And then we need the air gap. And the air gap can be filled either with air or with argon. And we can have double or triple glazing. Okay, so that's the glass. When you are reading this in the catalog, laminated glass, now you know what it is. And now we have this kind of so we have this kind of coatings. Okay, so there's another thing we can have in the glass, which are the coatings. Okay, so coatings are it's not the glass. So it's a treatment that we apply on the surface of the glass. It can be either the, well, usually when we're talking about glasses, we put names to the layers. Okay, if this is outdoors, this is layer number 1. This is number 2. Number 3. And number 4. Okay. So the coating, it's a treatment. It's a very thin layer of usually something made of some metals, chrome, or very heavy metals, but so thin that you can't notice. They are almost transparent. And then we can apply this coating on layer 1, 2, 3, or 4. Okay, so that depends. If we apply this on layer 1, this is out, and this is in. This is indoor environment, and that's out. Okay, so we have 1, 2, 3, 4, and usually we have to specify. Okay, I want this coating on base or on layer 2. Then they apply this on layer 2, or on layer 4, or layer 1. So this is so if you go to a site and you hear the glass providers or manufacturers, and oh, well, where do you want the coating? Layer 1, layer 2. So this is that's what they mean. Okay, and it matters. So those coatings are very, very thin, extremely thin layers. They can be transparent, or they can have a color. Okay, but they are something very thin and almost, well, it's almost transparent. Okay, so there's something applied here. They barely affect the visible transmittance, so you can see through it. But what kind of coatings do we have? We have 2 kinds of coatings. We have the solar control and the low emissivity coating. So those are the most popular coatings that we have in this glass industry. The low emissivity is always for winter. A low emissivity coating keeps heat inside the building. Okay, so we use this for cold countries in winter because we want to keep, we are heating up the air here and we don't want that heat to go through the window. So the low emissivity coating keeps the heat inside the building. And the solar control, it's like sunglasses. So we have to prevent the exterior sun from entering the building. So this is the 2 kind of coatings. There are more, but basically this is what we need. So depending on where we are, if we are in cold countries, we will use low emissivity coatings. If we are in cold countries, we will use the solar control. If we are in hot countries with a lot of sun hours and high outdoor temperature, we will use the solar control coating. Because basically it's like a sunglass. If we have a huge area of sun in a very warm country, we have a lot of solar heat, and we don't want that. So we need like sunglasses. So this is it. When you open the glass catalog, you will see solar control glass or low emissivity glass. You can apply both. You can have a solar control with low emissivity. You can have different coatings on different. You can have 2 different coatings on the same page, on the same surface. But you can have a low emissivity coating on layer 2. You can have a solar control on layer 3. But you never have 2 coatings on the same face. And that depends on what we want. New Hampshire, it's an excellent example because what do we need? In winter, we want the sun. We want the heat to stay in the building. So we need low emissivity coating. Do we have trouble in summer in New Hampshire? No. So we don't need a solar control coating outside. So in this building, we have this nice curtain wall on the south. It's transparent. It's not because the solar control coatings are dark or mirrors so that we reflect the light. Okay, just like sunglasses. So we don't have this kind of solar control coatings in New Hampshire, but we do have low emissivity coatings. In other places, what if we have cold winters and very hot summers? Can we have both? Yes, probably we can have both coating, but then the low emissivity usually is indoors, and the solar control usually is close to the outdoor. Okay. So if I were doing this, if I had to place both, if I had to place both, I would place low emissivity on layer 3 and solar control on layer 2. Okay, what do we want with the solar control? I want to keep the sun out. Okay, so with the solar control, I keep the sun out. With the low emissivity, I want to keep the heat in. Sorry, the heat in winter. Okay, so usually this is what we have. We don't apply coatings on layers 1 and 4 because those coatings are very. If I do this, if I scratch, I remove the coating. And I don't know this because coatings are transparent. So that's why coatings are protected and they are in the inner faces. So usually we apply solar control on layer 2, and usually we apply low emissivity on layer 3. There might be exceptions, but again, we have to deal with the glass manufacturer. We have to talk to them. Okay, what do you want? I want this. This is in New Hampshire. The use of the building is this. But we don't have summer classes because we don't. Okay, so we don't have summer classes. You don't need the solar control. No, I don't need the solar control. But it's very cold. Okay, so you need the low emissivity. Yes, I do. But what about in triple glazing? Do we have the solar control here, the low emissivity there, 2 cavities with argons? So there are a lot of combinations, and basically we have to deal and we have to talk to the glass manufacturer, to the granite state glass or whatever. But this is the first decision that we have to make. First, double or triple glazing. Then, if we need safety, laminated or non-laminated glass. In high-rise buildings, in outdoor windows, we need laminated glass for sure. And then the third decision is, do we need coatings or we don't? In cold countries, low emissivity coating. In warm countries with a lot of sun, solar control coatings. So this can be that straightforward, okay? But then depending on the use of the building, depending on many things, this might change. But okay, and how can we understand that we have a low emissivity in solar control? Low emissivity coating affects the U value. With low emissivity, the U value is low. With solar control, it affects the solar heat gain coefficient. Solar control coatings means that we have a solar heat gain coefficient very low. Okay. So what do I want in New Hampshire? In New Hampshire, I want to keep the heat in, or in Hartford, or in New England, because it's the weather is almost the same. So I want to keep the heat inside the building, and I want to maximize the heat gains, especially in southern windows. So I want a very low U value, very low. And a high solar heat gain coefficient. But I want this in King, New Hampshire. In Miami, probably I'm not, the U value is not that important because it's warm outside. And we need a very low solar heat gain coefficient because I have a lot of sun and I want to keep the sun outside the building. Okay, so this is what I need. So that means that I need a low visibility coatings and I wouldn't need a solar control coating. But can I say to the manufacturer, okay, give me this glass, I want the U value to be 0.1 and the solar heat gain coefficient to be 0.9. Can I do that? No, I can't. So that's why I have to go to the catalogs. We have tools and resources. Do we have technical literature? I want the technical. I want technical data for glass. Technical data sheet. Yeah, so this is what I need. This is for Guardian. Center. Let's download this. And we always have a nice fancy building with our vision. Okay, but this is what I want. Okay, so this is the Guardian catalog, and this is a double glazing, as you can see. This is the exterior, this is the interior, and what is this? I don't know, but there should be demanding performance, sonic climate. Anyway, here they will explain why they put a coating here on layer 2 and another one on layer 4. I told you that they don't use to do this. Doing this, they don't apply coatings on layer 4 interior, but apparently they do. But this is what I want. I want the U value and the solar heat gain coefficient. Here we have air and argon. Usually the argon values are always better than the air values. And for the solar heat gain coefficient, here we have 0.26, 0.38, 0.16. This is very low solar heat gain coefficient. 0.1, 0.2. Only 10 or 20% of the sun enters the building. So those are like sunglasses, very dark glasses or mirror. So we don't do this. What about the U value? The U value, we have 0.2 or with argon, 0.23, 0.24 with air. Okay, so usually argon is always better, but I don't know if it's worth it because it's much more expensive and that affects only the second decimal. Okay, depends. But we have more options. Okay, so we have solar heat gain coefficients. Those are probably they all have solar control because they are too low. And the U values, they all have, well, here we only have, probably this is the solar control. Let me see, we have something else. Okay, if this is the catalog that we have, and now we have to decide. Look at the U value. The U value is 0.24. The original U value was 0.8. Okay, so 0.8 is probably double glass without low emissivity coatings. So if we put a 0.2 U value on windows, we will reduce this a lot. But at the same time, I need a catalog because I need the solar heat gain coefficient. So solar heat gain coefficients here are very low. Okay, so we have this aspect. These are like mirrors. From outside, they are not transparent though. So do I want this? Well, I know. But those are very low. Okay, so I can use this one. Probably this is the best that I can find in this catalog. The U value is 0.2. It's one of the lowest. And the solar heat gain coefficient is the highest. It's 0.38, almost 1.4. Okay, so here I have to type 0.4. What I want is something that it has the lowest U value and it has the highest solar heat gain coefficient. So if you can find something with this, you have to let me know, and I would appreciate that if you find an actual catalog. Let me see, we have something else here. Custom coatings, this sun guard. Well, when we have the word sun, means that we all have solar control layers. Okay, so here they explain that. And here we have the U factor. Well, here the U factor is quite high, it's 0.8, so we don't want that. And the solar heat gain coefficient is 0.4. Okay, so there are thousands of possibilities on this website. Okay, so each element here, we have a catalog with this. But that's what we need. We need to talk to the manufacturer, and then we have to see their catalogs. And what do you want? Okay, I want something like this. I want a very low U value and a very high solar heat gain coefficient. What do you have? And then you select the glass that you need. Okay, but here we don't calculate anything. We have to ask the company about the catalogs. Okay. So this is probably the most important decision in your project. What kind of glass we are using? Not in single family houses, because in single family houses, we don't have a lot of glass, but in commercial buildings, that will affect the total heating loads. And usually it always happens in life. The better the product, the more expensive the product is. So you have a lot of coatings, laminated glass, it will be extremely expensive. Okay, but that's what we have to do. You have to find the catalog, minimum U value, maximum solar heat gain coefficient. And now this U value will affect the thermal load. Okay, if with 0.2, this is 2246. If this is 0.8, now this value it's 8,900, whatever. Okay, so we can save a lot of energy by changing this number, the U factor. And then the solar heat gain coefficient will affect the heat gains. Okay, so if we're looking at the heat gains in January, what we want to do is to maximize this number, heat gains in January. So with 0.4, we have 106,000. If I type here 0.8, now I have 213,000. Okay, so a glass with a very low U value, 0.1, and a very high solar heat gain coefficient, 0.85, that will be the best. Okay, so if you can find the catalog with this, that would be the best option. 0.10, very low U value, 0.85, almost transparent. We have a lot of solar gains in January. This is when I want to have these solar gains. But what we have found so far, it's at 0.2, it's not bad. But this 0.4, it's too low. So I think with a 0.2 U value, you can find up to 0.6 or 0.65 solar heat gain coefficients. But again, if you don't, you can Google glass U value and solar heat gain. And you will have a lot of examples here from brochures. Okay, so here we select this one. Here, yeah, here this is an efficient window, and this is interesting because we have the Energy Star. This is the energy code, and the energy code of the United States. We have always this brand, the Energy Star. So this Energy Star, you have a label of certified by this Energy Star code. Okay, so when you find this logo, that means that it's a product that you can rely if you rely in the government of the United States again. But if you have this logo, that means that it's certified by this institution. So what do they recommend? If we are, so they have divided the country in different areas. So you have the northern, and then you have the north central, south central, or southern, basically the Caribbean or the Gulf of Mexico, sorry, and California, or what's this, New Mexico? Or, and Hawaii, of course. Okay, so what they say is that in the blue areas, in cold areas, we need, for windows, we need U values lower than 0.27, and solar heat gain coefficient more than whatever. Okay, so the solar heat gain coefficient should be as high as possible, and the U factor as low as possible. So this is what they recommend. And this is the kind of information that we find in our in the glass in the product itself. So we need something like this. And here we have the U factor and the solar heat gain coefficient. We can't calculate anything. We have to rely on this kind of information, and that comes from the manufacturer. And if we have this brand, the Energy Star, I think it's yeah, it's something that we have to. At least we know that those guys have not purchased the glass from the Alibaba website or whatever. They have a certification. Okay, so that's it. For us, if I have found this, here we meet the requirements from Energy Star. It's recommended more than 0.32, the solar heat gain coefficient, and less than 0.27, the U value. So this is 0.2 and 0.4. Okay, so we can do that, but it can be better, believe me. Okay, so we did this for the southern windows, and we have to do something similar for the rest of the orientation. Okay, so here we have the south, east, and north and west. I'm going to copy all these columns. And I'm going to insert the columns here. No, here. Okay. So between the south, and this is east. Here we have the area of eastern windows, whatever you have, 100 or whatever, the area, okay. We need the U value and the solar heat gain coefficient. We might have different windows in different orientations. In small buildings, it doesn't make sense, but in big buildings, it makes sense, okay? But we need, again, the information about the U value of the window and the solar heat gain coefficient. And we need the area of the eastern windows. And now this is the thing that I have to change, okay? So this first row, I'm going to highlight this because that comes from PV watts. So this first row comes from PV watts. And I have to change this for different orientations. This is the values that we get from the south, and those are the values. Now I have to type here the values that we get from the east. So I have to open PV watts. Later, this was in Hartford, Connecticut. And we are in Hartford, we go here. Okay, so remember that these four, 1, 2, 3, 4 fields, those are for the PV array. We're not dealing with the PV array yet. And then the tilt is the angle of the element. 0 is horizontal, 90 is vertical. So if we are dealing with vertical windows, this angle has to be always 90. And the azimuth is the angle with respect to the north. So here we have to, if we are working with the eastern windows, that angle should be 90. 180 is for the south, 0 is for the north. Okay, so let's type 90 because now we are working with eastern windows. So that's it. The only thing I have to change is the tilt and the azimuth. Go to results. And now here I have the results from the solar radiation on the east. So I have to type here different values. In January is 1.47, in February is 1.97, March 2.35, April 3.02, 3.3. Two, 3.03. In October 2.19, November 1.5, December 1.23. Okay, so I have typed these values in kilowatt hours per square meter, January, February. So I have typed this here. That was the south. This is the east. Okay. And well, basically, I don't have to do anything else because remember that the first row is just this one times 337. Here we just convert kilowatt hours square meter to BTU hours square feet. Okay, so make sure that we always have this cell and then times the 317. That's just for converting units. And that one is, okay, so I have to change that because that one is the value that we have here, the BTU hour feet square, times the area times the solar heat gain coefficient. I think in your class, we did two different rows, one to multiply this times the area and then times the solar heat gain coefficient. But here I've done it only once. Okay, so B59 is this one. And then this, I have to multiply this times the area of the windows times the solar heat gain coefficient. And if I want to drag this, I have to type dollar and dollar, dollar. I click OK. I drag everything here, and there you go. Okay. So that's it. Then I have to do the same with the northern and with the southern window. If we have, in this case, we only have the northern, the western, sorry. I know, in this case, we have east and we have south and west. Okay, so you have to do this. And if you don't have any east windows, you type here 0. in the area, and that's it. We don't have any thermal load. Okay, I'm going to do it again. I'm going to select everything here. Ctrl C. Well, I want this row too. Ctrl C, insert. So this is north. So in the northern windows, the area, it's whatever. Imagine that we have 100 feet. We have the U value and the solar heat gain coefficient. Now in this row, I have to type the values from the PV watts. So I go back to where are you taking a picture?
Yeah, you're good. You're good. Don't worry about it.
You want me to?
Thank you.
Okay. So on PV watts, I have to go back. If we have vertical windows, this is always 90. The azimuth for the north is 0. So I type 0 here. Go back to results, and now I have to type these results on my Excel file. We are in the north facade, and in January is 0.58, in February 0.76, 1.28, 1.373, 1.1. Okay. I type here the values from PV watts in the north, and this one is always converting units. It's the cell times 317, and this one I have to change this. So it's this cell times the area of the windows times the solar heat gain coefficient. And if I want to drag these numbers, I need to type $, $, $. There you go. And finally, for the West, I'm going to do it quickly. Now, I'm going to copy all these, copy, insert cells. I can delete all that. And now this is West. I have to go to the PV watts. If it's vertical, this is 90. If it's west, this is 270. Go back here, and now I have to type all these values there. January is 1.55. February 2.8. Well, sometimes, okay, it does like weird things, 1.03. Okay, sometimes Revit thinks too much. And when you type 3.1, it thinks that you want to write January the 3rd, and you don't, or whatever. Okay, so be careful with this, because I noticed that I have some mistakes here. Okay, so I didn't know this until now, but in April this has to be 3.04. 3.04, and it keeps doing this. Why? I have to format cells, and yeah, for some reason it has selected day and month. I don't want that. I want the number. Okay. If we do this, format cells, select number. Okay, be careful, because it has happened. And yeah, sometimes computers think on their own, and they think that they're smarter than us, and probably they are right sometimes, but sometimes they're not. Number. Well, this is not 44,000. I have to check that. And it's not. Okay, so there's an issue in the East in April and May. Okay, East is 90. And April is 302 and 323. 3.02. It keeps doing this. I format this as a number. And this is the 3.23. And so that's a number. Okay, well, be careful, because sometimes it happens. So make sure that here we have these values. So make sure that this is always the cell times 317 to convert units. And here we have to multiply this times first the area times solar heat gain coefficient and dollars. Dollar. And drag. There you go. Okay, so now I have the thermal loads in the south, the thermal loads in the east. If I have zero, if I don't have any windows, I type 0 as the area of eastern windows, and I don't have any values. If I have 0 in the area of northern windows, I don't have anything. And in this exercise, we have something in the southern and western elevations. I have windows there, so I should have values for the south and the west. So here we have the total thermal loads. At some point, the total thermal loads of windows. So here, well, check this. If we click here, this is the U value times the area of the windows. And since I typed the dollar from the beginning, I have indoor minus outdoor temperature. Okay. but check that that is the right formula. It has to be always U value, area of windows, and then indoor minus outdoor temperature. So the total thermal loads for windows, I have to type this cell plus this plus this plus this. And now this is the total thermal loads for the windows. Okay. So now I have to, I have done this. I have added thermal insulation on the walls. I have thermal insulation on the roof. I have thermal insulation on the basement. Now we have 2 inches on this wall. I'm not doing anything with the heat recovery because I explained last time what we did with the heat recovery. So here you have to type the efficiency of your heat recovery. And on the first one, the efficiency of your heat recovery should be 0. Okay, so but we did this last time, and we divided this in different floors: basement and first, second and third. So what are the conclusions now? So I have to open 2 different okay, so I have this one with without any improvements, and now on the PowerPoint, the summary is first current state. Okay, so this is what we have found when we get our buildings. We have the walls, the total thermal loads through the walls is this value, 6,640. BTU hour. What's the first state? The thermal load through the walls with 2 more inches of thermal insulation, it's 5181. BTU hours. What's next? The roof. The current state of the roof was 1302. Don't forget units, BTU hour. What about the roofs in the reversed state? So with 2 more inches of thermal insulation, the roofs, it's 943. What's next? Windows. Windows. Or let's do the basement first. The basement, the original state, it was 3494. And with the new thermal insulation on the basement, we have notice the doors, basement 1830. And finally, windows. So for the windows, the original thing was, I think I deleted it. Okay, So I remember, because I mixed this up, but I remember that it was around 16,000 BTU hour. So what's the new thermal load through the windows? Now it's this. Well, you have to check the areas, because we have 216 in the south elevation and 220 in the west elevation. Okay, but now it's it should be much lower. So now it's 4,534. Okay. And finally, we have ventilation loads. First, without heat recovery, and second, with the heat recovery. With the heat recovery. And now you have to add all this up, and we need the total here and the total there. Okay, so each student will have a different total, because you have to do this based on your. Oh, it's written here. Let's read the assignment. Okay, so the heat recovery that you have to use is 60 plus X. So it depends on again on your ID number. So I told you that heat recovery efficiencies go from 60 to 70. So in your case, we'll go from 60 to 69. Okay, so that will be the heat recovery, but you will have different values for heating loads when you are using the heat recovery. With the ventilation with heat recovery, your value should be different, because it depends on that efficiency. Okay. So that's the conclusion to this. Well, basically, now we need two pages like this. We need a page like this for the original, and we need another page like that for the refurbished. And then this is the summary. So the original building, your first analysis is this with the total, and your second analysis is this with the total. And finally, if it doesn't fit here, we have to calculate the savings. What are the savings? First analysis or current. And we are going to calculate the savings in energy and money. So what are the savings, or what is the energy that we consume in the current state? Is the total BTU per hour times, if this is a residential building, so we can assume that the residential building is occupied 24 hours. So 24 hours. Okay. And we are doing this for a day in January. Okay, so this analysis is just for a single day in January. Then we have to do this 365 days. So we have to do the same thing 365 times. We're not going to do it. We have software to do that. Okay, but at least you need to understand that we are doing this in a day. So the total BTU hour times 24 hours, which is whatever. Okay, so we can add all these up. Do you have any values, or have you done it? Any of you? Not yet. Let's see. I think the ventilation without the heat recovery was okay, 42. Okay, so let's do this like a 42,000. And the ventilation with the heat recovery, it was 17. Okay, again, those numbers are my numbers. You might have other numbers, so don't take this for. But if we do this calculation, we have 42,000 plus 16,000 plus 34 plus esto plus. Okay, so the total can be around 69,000. Okay, around 69,000 BTU hour. Good. So what's the total energy? 69,000 times 24. So that will be 69,000 times 24. Ooh, a huge number, 1,601,656,000 BTU. Okay, so we are talking about the daily energy. So one day in January, we have this energy consumption. So it's the total heating load that we need times 24. Now we have the refurbished. The refurbished is the total, again, is the total BTU hour times 24. So what's the total? This 17,000 plus 4,934 plus 1,830 plus 943 plus 5,181. Okay, so around 29,800. Okay, so around 30,000 BTU hours. So this is 30,000 times 24 equals 720,000 BTU. We're not done yet because I have to consider solar heat gains. Yep, we did that on Tuesday, and you thought that I had forgotten? No, I haven't. So what are the solar heat gains? The solar heat gains are in one day in January. Okay, so what was that? It was the total southern. No, it's not the total southern thermal loads. We are dealing with one day in January, so we're working with this. This is BTU day. So this is this number. And then what's the daily heat gain in January we have this, the last cell on January. We have 0 because we don't have any windows in the north, okay? Then on the east, it's the same cell in January. We don't have any windows in the east. And here, I didn't include this cell. So, okay, this is the right one, it's 6 cell. So what are the total heat gains? Here we have 106, 816. Plus the heat gains on the west facade, it's 43,238. So this is 106,816 plus 43,238. Okay, so this is 150 or 54. 150 or 54. Okay. So for the refurbished state, I'm going to use a different color. What is the total consumption? Total daily consumption in January. So it's this, those are my heat losses, minus, this is BTU, my heat gains. Okay, so this is 720,000 minus 150,000. So this is 569,946. BTU. So this is the number that I have to compare to the number of my original state. Okay. What are my savings? The savings are the original number minus the second one divided by the original one.